Section 5.2, we're taking a look today at the rest of multiplication and division of integers. And we are on Theorem 5.6. Whoops. All right, Theorem 5.6. For every integer a, negative 1 times a is equal to negative a. So in other words, negative 1 multiplied will give you the opposite sign of whatever a was to begin with. We've talked through a couple different observations of this with absolute values as well that look very similar to this one. So some of you are like, well, didn't we already talk about that? It was very similar when we looked at this before. All right, the next one is integers. If you have integers a and b, if you have a negative a times a positive b, that is a negative of a times b. And it looks like, in some sense there, you can think about that kind of as a associative property almost, right? If the negative were interpreted as a negative 1 and you reassociated the parentheses. The second one, when you multiply negative a times negative b, you get ab. Okay, the negatives cancel one another out. And then the last one is an example of the distributive property. So a times b minus c is ab minus ac, and b minus c times a is ba minus ca. So these are all things that you know, and that you know they work this way. And now we have the theorems to support that, if you will. All right, so the last thing that we're going to look at then is integer division and a few things with inequalities. All right, so first integer division, and we've seen this definition before. We saw it with whole numbers, but it looks very similar for integers. For all integers a and b, a divided by b is the unique number c if it exists such that a is equal to bc. Okay, fill those in and then I'll show you a number example and you'll be like, oh yeah, obviously that's true. Because numbers help us. So if we had, whoops, I need to get a different color. Okay, so if we had 6 divided by, or you know, we'll make it negative 6 divided by 2. This is equal to some number, and you know what the number is. What's the number? Negative 3. Okay, the reason that it's equal to negative 3 is because negative 6 is equal to 2 times that negative 3. And that's all this says, is that if you were to change this, this is like a fact family, if you were to change this into its corresponding integer multiplication problem and fill in the blank, that blank that you filled in would be the answer to the division problem. Okay, the reason that 6 divided by 2 or negative 6 divided by negative 2 is negative 6 divided by 2 is negative 3 is because negative 6 is equal to 2 times negative 3. Divisibility for integers. If a divided by b is a unique integer, then we would say that a is divisible by b. Now we did this in chapter 4. We talked about divisibility. Equivalently, if a is divisible by b, we say that b divides a, and we are now all fairly comfortable anyway with that notation, right? We've seen it more than once. We saw it before only with whole numbers. So this slide's basically telling you, this theorem's basically telling you that everything we did with whole numbers is true for integers as well. Okay? So the reason that negative 6 is divisible by 2 is because 2 divides 6. 2 divides negative 6. Okay? So it works the same way. The last thing is that we're looking at is inequalities. So for all integers a and b, a is less than b, written with the a, the less than inequality symbol, b. If and, that should say and, only if there exists a positive integer k such that a plus k equals b. Again, we saw this definition already with whole numbers. But the reason, for instance, that negative 1 is less than 1 is because there is a number I can add to negative 1 to equal 1. What number is that? +2. It is +2. And that satisfies the fact that it's supposed to be a positive integer that we're adding, not a negative one, because that actually won't work at all. Okay, so the reason that it's less than it is because if I add something to it, I can actually equal the other value.
Would the opposite work the other way?
Like what?
It was like, if you had an, like it was greater integer?
Yeah, we could make a statement like this, the same if you would prefer, about greater than. And you can either make the statement about greater than and do addition to the smaller value,
Okay.
or subtraction to the larger one.
Okay.
So we can work this out as a less than statement, a greater than statement, an addition statement, or a subtraction statement, just depending on what order we're putting things in. Yep. All right, last set of theorems. For integers a and b, a is less than b, or equivalently b is greater than a, if and only if b minus a is equal to a positive integer. In other words, if you take a bigger number minus a smaller number, you always end up with a positive number. And it's true even if you're working with negatives. So let me show you what I mean. Let's say, for instance, we had -3 is less than -5. I didn't write that right. Next to -1, 2. Well, -2. -3 is less than -2. Let's go with that one. So why is that? Well, we're saying that this one's bigger, correct? So this is my larger one. And this will be true if and only if I can take the larger value minus the smaller value and end up with a positive number. So what happens when I do -2 minus a -3? Yeah, you get -2 plus a 3, which is a 1. And lo and behold, you end up with a positive number when you subtract, no matter whether the numbers are positive or negative to start with. Bigger minus smaller equals a positive number when you're done. And so I don't have any idea why I have blanks in here on number 5, because yours don't even have blanks. X, Y, whoops. X, Y, and N. For all integers, X, Y, and N. It doesn't even phrase it the same way as what I've got in your notes. Okay, pretend anyway. Doesn't matter. Yours are in there, right? Let X and Y be and N be integers. If X is less than Y, then X plus N is less than Y plus N. Correct? Okay. So I know we've done this before with whole numbers, but the idea in the picture that I always imagine is the two of us were standing up here at front, and one of them's shorter than the other one, and we put 2-inch heels on each of us. Doesn't change the difference in our heights, right? You've added a little bit of height to each one of us. We both step on the same step stool. We both stand up on the desk, whatever. Our difference in heights is the same. So we're still the same person's shorter than the same person that was taller. All right, if X is less than Y, then -X is actually greater than -Y. And numbers are helpful here to think about, but you certainly can do it without them. So let me just use some numbers. Let's say that 2 is less than 5. Then this would make -2 and -5. If you think from a number line perspective, you will agree that -2 is in fact greater than -5, right? And you probably remember something like this, is that when you multiply or divide by a negative, you change the direction of the inequality, right? So this one was less than, and it's now greater than, because in effect, I multiplied both sides by -1. All right, the next one tells us that if X is less than Y and N is positive, then Xn is less than Yn. Okay, in other words, if I multiply the values by positive numbers, the inequality stays the same. All right? So imagine if you had a piece of paper, an image on a piece of paper that was 2 inches tall, and you had an image on a piece of paper that was 3 inches tall, and you enlarged them, right, in a copier. Okay? Well, this image that was 2 inches tall, when it's enlarged by the same value that you enlarged the other one by, it's still going to be smaller, right? That's all this is saying. If you multiply it by some kind of a scale factor, you enlarge it, if you shrink it, it doesn't make any difference. It's still going to be smaller than the other value. And then the last one says that if the X is less than Y and N is less than 0, well, if you multiply by a number that's less than 0, again, your inequality changes. So this is Xn is greater than Yn. And again, let me just use some example of numbers so you can see it happen. So we'll use the same 2 is less than 5 here, and we will use that N is less than 0. So let's just say N is a -3. So if I do 2 times -3, and if I do 5 times -3, what is 2 times -3? -6. And 5 times -3? -15. And which one's bigger? The -6 is bigger. It's closer to the origin, right? So it is bigger. It's closer, or it's further to the right-hand side of a number line if you prefer. So we get an example where we can see one happening.
Wait, so the sign changed?
The sign changed, and the reason the sign changed is because the negative value. So just like right here, the sign changed as well, again, because we multiplied by something that was negative. Okay, we have two examples of solving equations. You do not have to solve these in a traditional algebra format. That's not what you're asked to do. You're just trying to find numbers that make it true. Okay? So it doesn't mean that you can't solve it traditional algebra, but I know that some of you are not fond of traditional algebra. And so if that's you, don't feel like you have to do this sort of like you would have in a college algebra class. So I'm going to show you a couple different ways to think about it, kind of depending on your perspective of that algebra concept I just mentioned. So I'm first going to talk about it from a non-algebra standpoint. Okay? What I'd like you to do is to notice that this quantity and this quantity are the same, right? Well, the only way that I'm going to take -5 and multiply it by something and still get -5 is if the thing I multiplied it by is equal to what? 1. That's the multiplicative identity property. This thing that I'm multiplying this by, the x minus 3, must be equal to 1. That is the only way that's possible, right? So if I do that now, what number would I need to subtract 3 from to get 1? 4. This value must be 4, because 4 minus 3 is 1. Okay? We're thinking of it sort of as a process of elimination. If you think about it from an algebra standpoint, and some of you I know think that way too, so let's actually work this through. You can do one of two things with the -5 on the left. One thing you could do is you could distribute -5 through the x minus 3. The other thing you could do is you could divide both sides by -5. Most of you probably would look at that and distribute, so I'm going to show you what it looks like when you distribute. If you multiply it, or if you divide it to the other side, you just automatically get to here, by the way. Okay, so if we distribute, then we're going to get -5 times x is -5x. And then I need -5 times -3, which is what? Positive 15. Now, if you'll remember from an algebra standpoint, we always do the addition or subtraction first. So we're going to subtract 15, because the 15 that's positive needs to had a -15 added to it to cancel. So this piece cancels. I'm left with -5x on the left, and I'm left with, what's -5 minus 15? -20, exactly. And then I've got -5 times x, and the opposite of multiplication is division, so I'm going to divide by -5. So I have x on the left. What is -20 divided by -5? Positive 4. Okay. It doesn't matter to me which of those approaches you like. They work just fine either way. Now the next one, probably solving it with algebra, which we will do, I'll show you, makes this one look a little bit more complicated because they're squared. I mean, right? Like there's something about this that feels like, maybe I don't want to do it that way. What I do want you to notice though is what happens when you square something. It multiplies the number by itself. What happens to the sign? It's always positive. Okay, so these are always some different things that we want to think about. Notice what you have inside of this particular equation. X minus 1 and 1 minus x. What happens when you subtract two numbers? These are the same numbers, right? X is the same as x, 1 is the same as 1, and you're just subtracting them in different orders. What do you get? 5 minus 3, 3 minus 5. 7 minus 3, 3 minus 7. You get the same number, but opposite signs. Are you guys with me? So the fact that you have x minus 1 and 1 minus x and they're exactly the same means that these two quantities are already equal except for the signs. Correct? One of the signs is going to be positive, the other one's going to be negative, depending on what x is. But then we're going to square them. So it doesn't matter. So this is actually true for all integers. There are no numbers that we can't let x be here to make this work. Because these two quantities are the same value and opposite signs.
Is it just when they're square that they're positive, or when you do any exponents?
It's when it's an even powered exponent.
Okay.
Yeah, so if it were squared, fourth, sixth power, those would all work, but if it were an odd power, it wouldn't. The odd power would preserve whatever sign it was. And then these signs right here make both positive. That's it. They make both positive. Let me show you from, there's a lot of reasoning we just did with that. Wouldn't you agree? There really was. It looks like we didn't do very much and we got an answer pretty quickly, but that's partially because I led you through it. I sort of I told you the answer without telling you the answer. Leading questions, that's what those were, leading questions. Don't let a police officer ask you leading questions. That's probably a bad idea. Okay, those were leading questions. A lawyer, we don't want leading questions. But let me show you what it would be or what it would look like if you were doing this in terms of algebra. So in terms of algebra, we would have x minus 1 times x minus 1 on the left, and we'd have 1 minus x times 1 minus x on the right. Is everybody good so far? Now, when you're multiplying, you have to multiply the first terms, that's x squared. The outer terms, that's minus x. The inner terms, that's minus x. And the last terms, that's plus 1.
That's foiling.
And it's foiling. It's exactly right. So that's first, outer, inner, last. It's also called distribution, right? That's a distributive property. On the right side, we multiply the first terms, that's 1. We do our last terms, or outer terms, which is negative x. My inner terms is negative x. And then my last terms is plus x squared. And very quickly, when we clean this up, what do we see happen? They're exactly the same on both sides. Do you guys see that? Well, if they're exactly the same on both sides, then it doesn't matter what I let x be, because it's going to be plugged into the same exact expression. I can't change it then. The left side will always equal the right side. So x would be all integers. And part of the reason I wanted to show you both of these is also because even if you don't like the algebra, if you can't go through the reasoning, you still have that backup algebra approach. Some of the algebra is cleaner and simpler than others. Some of it's more complicated. It kind of depends on the problem.